So to begin with, I'm going to show you the effects of the proportional control gain. So in the previous video, you saw the effect of the proportional control gain where we select a specific value to give us a stable or an unstable value, or a range between, say for example, kp equals 0 all the way up to a value that will give us a stable system. I'll then introduce you to the rules of root locus. So this effect of the rules of root locus is going to show us the path of the path of the poles on the z-plane as we increase the proportional control gain from open loop pole positions where kp equal to 0 all the way up to kp, well, all the way up to infinity. So I'll run you through the 6 rules that we've got here, and the 6 most basic rules that you need to be able to draw the path of the root loci, and then I'll show you then using Matlab. Then we've got a quick checking question and then summary. So hopefully at the end of this lecture you understand the key learning points. You're able to explain the result of varying the proportional control gain and what this does on the system performance, and also apply the rules of root locus to determine the path of the root loci. So in terms of the effect of the proportional control gain, so here just to kind of get you back into kind of a feedback control system. So here we've got the pure discrete time equivalent of a sampled data control system. So consider the case initially where the discrete time model, so g of z, we effectively got a mathematical model of, if you remember from one of the earlier videos, where on the introduction to model-based design for embedded control, you would have seen a video of this pipe climber climbing up and down a pipe and stopping at specific locations on the pipe, so it had kind of distance control. So that effectively uses a feedback control system that looks a little bit like this, where we're effectively measuring the output, which in this case we'll be using a sensor, some sort of distance sensor, to measure from this point to the ground. We've got our reference, that's effectively where we want the pipe climber to stop on the pipe, and then we form an error when there's a difference between where we are and what we want. And then the controller, in this case, at the moment, we're just going to look at kp, but in a couple of lectures' time, we will be introducing proportional, which this is. Well, not introducing proportional, but as well as proportional, we'll have integral and derivative. And then here is the control action, which effectively is going to put more or less power into the actuator, which in this case is a DC motor, to increase or decrease the speed, or to stop the motor, reduce it altogether when it's got to stop at a specific location. So that's your feedback control system. So if we're looking at the transfer function for the closed loop system, this is kind of the form that we're given, where g of z, we could g of z could equal to n of z over d of z, where numerator in this case is effectively this value here, so, and your denominator is this. So substitute in g of z is equal to that, and then then multiply by d of z. Okay, so then we effectively just end up with kp over n of z, because the d of z cancel, the d of z cancel here, and obviously 1 multiplied by d of z. So we end up with d of z plus kp n of z. So that there is our closed loop transfer function. So it just saves you a step when you're doing the calculations by hand. So here we can straight away get the feedback, the closed loop transfer function. So we can substitute in the numerator, the denominator, and the numerator again there. Kp though at the moment is unknown, and what I've done here is I've got g of z, where I've effectively got a discretized transfer function here, g of z to represent the motion of the pipe climber, and I've discretized it with a sampling interval of 1 second, so it gives me this transfer function here. You'll notice it's got real roots, so it's going to give me a kind of a response that's got no overshoot. So what I've done here is I've initially run 3 different kp values in the system. So kp 01, 04 and 07. And then using this g of z, so where I've just inputted here the numerator and the denominator. Sorry, I was cross-referencing from here to there, but note this is closed loop transfer function here, closed loop, closed loop. This here is your open loop transfer function. So numerator in, denominator, and then what I've done then is just vary the kp between these values, and if you were to do the maths, you would, with a kp value of 0.1, using the numerator and denominator here, you would end up with a closed loop transfer function given by this. Okay, then what I've done is I've subjected it to a unit step input. So effectively 1 over s, or 1 in the time domain, and that's the system response that I get there. And then you notice here I've increased the proportional control gain, 0.1, 0.4, 0.7, and what you'll notice is, if we're looking here at the system response, is getting more and more oscillation on it. And that might not be typical performance of the pipe climbing, because it might be in actual practice that you don't really get much oscillation. But maybe another practical example to think of is a suspension system, or some other mechanical systems. What you'll also notice is, if you were looking here at the pole 0 map, so your Z plane, you'll notice that your 0 here, okay, 0 being the, if you effectively equate this to 0, you notice your 0 here does not change as your KP value changes. What you will notice though is that your poles are moving. So your poles are moving to the left as you increase the proportional control gain. Okay, and as I told you in one of the previous videos when we looked at the Z plane, I told you that your location here is a function of TS, and obviously in this case T sampling interval is fixed, 1 second. But what you'll notice is that the actual pole location, okay, the system isn't changing, but the proportional control gain is changing that overall characteristics of the transfer function. So in terms of, if you were to work out the roots of these, and these, obviously that will give you your poles, and you notice here they are changing, okay, and that's due to the proportional control gain. What it's doing is it's effectively moving the poles to the left, and it kind of like looks like a little bit of a circle. And if you were to continue to increase the poles, you would notice that at some point the poles would exit the unit circle, and hence the system would become unstable. So what I'm going to introduce you now to is the rules of root locus, because what we saw in the previous video was, as we increase the proportional control gain, the path or the location of the poles is changing. So what the root locus enables us to do is to explore the path of the poles changing as you increase the proportional control gain. So one thing you need to remember is, when you're doing the rules of root locuses, the starting point when you're doing the rules is just the open loop transfer function, and this can be in continuous or discrete time. Okay, so always use the open loop transfer function. So that's what the rules of root locus allows us to do. And what it assumes the following. So it assumes that you've actually got a negative unity feedback, okay, when using the rules. So unity, i.e. an ideal sensor, and negative because you've got negative feedback. So you're comparing the reference to what you've measured. And you've got a proportional control gain, i.e. here K subscript P, in the feed forward path. So effectively this configuration that you've got here. So the rule 1, and nice simple rule. First rule really to remember is that the Z plane is, like the S plane, is symmetrical about the real axis. So whatever happens up here about the real axis is repeated down here. So what I've done to begin with is I've got this following transfer function. So just for an example that I'm going to run through, I've got this transfer function here, and I've worked out what the poles are. Okay, these just equal to 0. So effectively we've got first pole, second pole, and then the 0 where Z is equal to minus 0.2561 divided by 1.3872, and that will give me my 0. So I've got my poles and my 0 on the Z plane. So rule 2, this effectively tells us where we, in terms of the root loci, if we sit on a segment of the root loci is part of certain bits on the root loci. So a segment of the real axis is part of the root loci if you're along here, this rule applies, at a given location along the real axis, the total number of poles and zeros to the right is odd. Okay, it's quite a simple rule, but if you can see my mouse cursor now, at the moment there's no poles and no zeros to the right. Okay, now, oh, stop, we've got 1 pole to the right and no 0. Okay, so that's an odd number. So we're on the root loci there. And then if I move here, oh, we've got now 2 poles and no zeros to the right. Okay, that is an even number. So hence we're not on the root loci. And then if I keep moving, okay, now I've got 1 pole, I've got 2 poles, sorry, and 1 0. So what that tells me is that I am on the root loci because the sum of that is 3. So, and again, if you go back to the rule, if the total number of poles and zeros to the right is odd, you're on the root loci. So what this is telling me really is something's going to happen in terms of these poles are going to move together, and yes, they're going to break away, and then we'll see on the next rule anyway. So if we look at rule 3, so the relative degree, this effectively tells us the number of branches that terminate at an infinity. And to use the formula, the relative degree is effectively given by n take away m, where n is the number of poles, and m is the number of zeros. Because in the case of the root loci, when you've got the root loci, so, and imagine it just relates to when you're increasing your proportional control gain, what's going to happen is eventually, kp starting at 0, what must happen is that the poles must either go to infinity or be captured by a 0. Okay, so it's either that you've got to have poles going to infinity or going to or being captured by a 0 or terminating at 0. So if we consider again this example 1, we consider the same transfer function. We've got two poles, 1 0. So our relative degree is 1. So that tells us that 1 pole is going to go into infinity, or 1 branch, is going to go to infinity, and 1 is going to go to 0. So you can see now what I've done is I've added arrows on here, because I know that something's going to happen here, and 1's going to end up going to the 0, because this is what it tells us. Because one definitely goes to infinity. So one of these here, one of the poles, the root loci is going to end up going to minus infinity, and 1 is going to end up going to it must end up going to the 0. So rule 4. So this is effectively the breakaway angle. So the breakaway angle is given by this equation, which is 360 degrees divided by the relative degree. So it's quite simple. So in this case, obviously our relative degree was 1, so our breakaway angle is 360. So you can see here, I've just drawn this blue line on here, because like I said, what I kind of anticipated, that these two were going to come together, they're going to break away, and 1 is going to effectively rejoin somewhere here. 1's going to go to a 0, the other one's going to break away, and it'll be symmetrical, remember, and then shoot off down to infinity, minus infinity. So the final rule, not the final rule that we're considering within this lecture, there is another one, is effectively to determine the radius of the circle. So the radius of the circle, effectively the path of the root loci when it breaks away from the 2 poles, and this is formed as a circle around the 0. Okay, so you take the radius around the 0, and the equation is given by the geometry mean of the distances between the 0, so this 0 and this pole, and this 0 and this pole. So the equation is effectively just r equals square root of d1 multiplied by d2. So again, if I just work out, no, not again, but if I just work out the distances between these, so you'll see 0.0498 and 0.1846. That's effectively the distance, and then minus this minus term, and then this, the distance is that. Take square root of that, and then I work out the radius is, in this case, 0.2738. And just note, I'm working here to 4 decimal places. So then what I can do, put the radius on, and then, add the radius. And then what this is now telling me is, I know exactly my path for the root loci. So this pole here is going to come, okay, it doesn't matter which way you go, that one's going to go up, that one's going to go up, whichever, it doesn't matter, it's symmetrical anyway. So if this pole is going to come, it's going to break away approximately midway there. Don't worry too much about it. There is rules whereby you can look at that, but there's tools such as Matlab that I'll get onto in a minute that enable you to explore these sort of things much better. So break away, it's going to do this, and then it's going to join the real axis again, and then go to 0. This one here is going to then break away, and then it's then going to shoot off to minus infinity. And this is what's happening when you increase the proportional control gain on the feedback control system. Okay, with root loci, we just use the open loop transfer function, but it's assuming that we've got negative unity feedback proportional control gain in the feed forward path. And that is the path of what's going to happen in terms of your system performance. So as you increase that proportional control gain from Kp equals 0 to a given value here, you know that your system performance is going to change. Because if you recall, you have lines of damping ratio, lines of natural frequency, and obviously as you change your poles, as you change your Kp, your pole location changes, and that relates to natural frequency and damping ratio, i.e. is going to give you different system performance. So then rule 6 is the use of the jury test to determine effectively the range for which your system is stable. So again, well, not again, but I haven't put the calculations here, but if you want to do so, please feel free to do so in your own time. But if you were to undertake the calculations, you would see that Kp is equal to 1.05. Hence, we need a Kp that's greater than 0. Okay, that's always the case, and a value that's less than 1.05. Okay, so less than 1.05 to remove us from being on the imaginary axis, because we don't want a system that's marginally stable. So that is there, the 6 rules. So now what I've got here is, because at the beginning of the lecture we had this. So I showed you, we've used the same transfer function all the way through. So we had this closed loop transfer function here. However, what we did when we went through the rules of root locus is we just used the open loop transfer function. But here I applied a step input and also looked at the poles on the Z plane to show the location. So this here is giving us effectively the same result as if we were just using the open loop transfer function going for the rules of root locus. So, and what you would notice is exactly the same effect. So you've just seen kind of like a circle where you had like your open loop poles, one broke away, went to the 0, another one broke away and then went off to infinity, minus infinity. So you can see like the circle here, which is very much the same as what we've just seen. So if I go back, I've got a short video now, because what we've got now is the root loci, or the root locus plotted in, the root locus here plotted in using Matlab. And you can see on the root loci, so I've got some details here, so you can see here where my pointer is now, the gain is 0, and you can see the pole location, you've got real poles, damping, it'll tell you what your expected overshoot is, so it's going to be 0 because you've got real poles, and then your frequency, so your natural frequency. Okay, so just to note that at the moment you're going to get no overshoot. The poles then become, you've got a pair of complex conjugate poles, and you can see your gain value is increasing, your poles are changing, and your damping is changing. Your overshoot is obviously changing, and as a result, and your frequency is changing. So you notice that one goes off then down to infinity, down to the 0, apologies. And then you'll notice the other one, and these are obviously in pairs, but here I'm just doing it to show you the effect of this. So if you can see that the natural frequency is decreasing or changing, and the overshoot, damping, and then you got up to this point where your gain value now is on the imaginary axis, on the unit circle, it's 1.05. So that's as you would expect, because when we worked out by hand, we worked out that a value less than that would give you a stable system. So hopefully that's it's giving you an insight into so from varying your proportional control gain, it changes your poles, changes your damping, it changes your natural frequency, and then one of the system performance criteria we're looking at is, in this case, is overshoot, that you can see it's having an effect on. So what I've got now is 2 questions for you to have a go at. So stop the video, have a go at these 2 questions. They're one here, you've got real poles, and then you've got here complex poles. So have a go at these 2 questions. So considering the following Z-form transfer function to determine the root locus using the rules. So in summary, I hope that you've understood the effect the proportional control gain on a closed loop control system has on the the system performance, and hopefully you've understood the things that have been detailed. So the effect that this has on the pole location, the z-plane, and also the system response. And the use of the rules of root locus have been detailed, allowing for the control system to be analysed when subject to a given proportional control gain value. Okay, and it's great doing them by hand. They give you initial insight in terms of the path of the root loci. However, if you want detail, you're better using a tool such as Matlab. So hopefully, key learning points, you're now able to explain the results of varying the proportional control gain and what this has on the system performance, and you're also able to apply the rules of root locus to determine the path of root loci. So if you have any questions, please feel free to email me. Thank you.